Ladies and gentlemen, the event will begin shortly. Please be seated and kindly turn off all cell smartphones available throughout the event. Your cooperation is kindly appreciated. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
as well as a advanced Ecole Centrale de Lille, and also at the Chile University of Chile and China, Tsinghua University. There is various positions that have been worked on different various universities. And also, his research interests include the techno-economics modeling of low carbon grids, multi-energy systems, energy system planning and capacity, and reliability and resilience of networks. He also involved more than 70 research projects worldwide and engaged in energy policy in the United Kingdom, Europe, Australia, and also author of several books on over 300 research publication and reports. Prof. Luigi is an IEEE Power and Society Distinguished Lecturer, editor of the IEEE Transaction on Power System, IEEE Transaction on Smart Grid, and also Open Energy, the convener of the C234 Working Group on Flexibility Provision from Distributed Energy Resources, and the past chair of the Working Group on Energy of the IEEE European Public Policy Initiative. So, Prof. Luigi will deliver his keynote speech on the flexibility, reliability, and resilience from distributed energy resources. Without further delay, I would like to call upon Prof. to deliver the speech.
Morning, everyone, and thanks for the kind introduction. It's a great pleasure and an honor to be here to be able to share some of our research that has been going on the past 10, 15 years, I would say, across the world. Many of the things I want to show you go back really to my time as University of Manchester. I spent time there. Then more recently at the University of Melbourne. Oh yeah, there's still lots of nice things happening with the University of Manchester. I'll show you. Now, I think I will, what you will see in the next 14 years pretty much is I will be recalling a lot of things that we've seen in the previous days and a number of things that previous keynote discussed, particularly how somehow there is a world that is changing and our understanding of the world is very, very limited. And I would like to start thinking that in reality, the future we're looking at goes back to the past. And I try to summarize this in best possible way by saying back to the future. Do you know what these two images are? Can you recognize this? So this one is the fuel cell that allowed the moon landing, and this one is the Hubble telescope that of course is powered by solar PV. So we talk about today. These are technologies, hydrogen and PV, and that are very much to homes. But no, that goes back really to space. This is to say that technologies evolve, change, will be there, will be needed. The problem is that we need to develop everything else around technologies. Like engineers can do big magic, or they can send the man to the moon. So certainly it won't be a technology problem to deliver low carbon energy system. The problem, as we know, is like technologies are there or will be there. The problem is how you do everything else. For example, in the context of so-called energy trilemma, where you need to deliver on decarbonization, of course, as the main driver, but also how do you guarantee reliability and affordability. In the good old times, it was all about trade-off between reliability and affordability. We want to keep costs down, but of course the lights on. Now, then we add the decarbonization component, so we move from a dilemma to trilemma. How difficult is it to bring everything together? Now, when I'm going to talk today, we start from reliability, because it's something that is very poorly understood, especially in the context of regulation policy makers. Whereas it's very easy to say on TV, I want cheap energy and I want clean energy, but then you have no idea about how power systems work. And the reality is that power systems have worked for 100 years in an impeccable way. It's like the greatest machine ever built. If you think of the reliability of the greatest machine, it's incredible. But now renewables really challenging system operation. So how do we operate and plan a new system? That's an unprecedented challenge for the current generation, future generation, and it's really poorly understood, especially when you look at technical problems like reliability. So if you look at how the system and the market is changing, or try to summarize like this nice picture, it's sort of prepared in some sort of with a very good colleague, it's Thomas Sapper, Inizio Zadia. And we try to summarize a little bit the idea that there is a system, there is a market, and then flexibility and somehow forms of control and reliability can come from different aspects for different parts of the value chain. But primarily, they really come from flexible generation units, and then of course they are interconnected. You can borrow and learn flexibility from to other regions. Now the system is changing significantly because the generation portfolio that was providing flexibility in the first place is changing dramatically, but also somehow the direction of flexibility is changing. Because if you think about it, historically, again, in the context of the value chain, it was all coming from transmission system. There would be a few hundred generating units providing flexibility and system control to a system on the distribution side that would be pretty much completely inflexible. There would be no form of control there. And we would rely a lot on redundancy, some redundancy on the transmission system, lots of redundancy on the distribution system. In fact, distribution, we won't even call it a distribution system, it was a distribution network, since it would be completely passive. And the way that you would solve the problem of the control of distribution networks basically would be by putting no control. It's like you design a very large distribution grid for worst case scenarios, so lots of redundancy, and then you're good. You don't put any control, and the system, the distribution network is completely inflexible and passive, and of course incredibly expensive too. However, all of this has allowed the system to operate very reliable for pretty much 100 years. Now there is a system that's changing significantly because of renewables on the transmission level, where conventional generators were and still are, but also there are more and more distributed technology that are now popping up at the edge of the grid, as was mentioned a few times yesterday by Wayne. So these are fundamental disruptions to the system you can see visually, because now there are new active systems appearing in a system designed to be passive. So when you look at now this idea of where do I find my flexibility with the new system, and with the fact that many of the traditional providers of flexibility are basically disappearing, because coal is getting out of the picture, gas, we see what's happening now. So how do we operate, how do we run a system reliably if the traditional flexibility sources would disappear? Who will provide flexibility? And if we do not find new sources of flexibility, what's going to happen? Well, what's going to happen, again, we don't have to imagine too much to understand what's going to happen if we don't fix the problem, or we find new ways. Of course, this has already happened. This has already happened.
Oh.
So we've seen this a few times. We've seen it for the first time probably in 2016 when there was the South Australia blackout. It was the first textbook example of how a system run on renewables would actually be in trouble if you do not operate in a proper way. And we saw a little bit of everything in blackouts. And now we're seeing more and more. So what happened in Texas, we're seeing where there are a number of events, really, to be too long now to list them, that just happened in the past 5 minutes. Of course, as I said, it's not a technology problem. And if the technology is not there, it will be created. So for engineers, it's never a problem. For engineers, every time that there is an issue, actually, there is a solution that can bring innovation and great potential to change the world, as it has been done by a modern Tesla. This is like the old Tesla changed the world. Now, like the modern Tesla is again trying to change the world. And you know the story, for example, it's not a story, I mean, it's reality that after the South Australia blackout, they literally promised the South Australian government to build a 100 megawatt battery in 100 days. Otherwise, if he couldn't make it, it would have been delivered for free. And he did it. So, this battery is now performed incredibly well. This is like the most extraordinary sort of technology that we have in the world, probably. If you look at a number of reports to the performance of this battery, it's just astounding. As a young student 20 years ago, I spent lots of time trying to understand how a battery would work. Mathematical modeling, the controls, and how do you model the binary variables? What can a battery shift from injection to absorption? How can you do this? How long does it take? Well, because they didn't exist. You pretty much have to be very imaginative in understanding the potential. But of course, whatever you would do would be wrong. Like unfortunately, many of our papers are wrong. I would say was words. Then you see technology, how it operates in the real world, and technology actually operates beyond any expectation. It's like it's just I can't stress enough how incredible it really has been to see this technology operating in the Australian system. And now a system that is very high on renewables is actually being managed with hundreds of megawatts of batteries throughout the system, frequency control, and a number of other services. So somehow in the relatively short term, the transition is being managed with some batteries, like new technologies, and of course relying also on old batteries, old type of batteries. Pump hydro that somehow has been there for some time. If we wish, probably this is the only electricity storage system that we've ever had, because it's the cheapest form and somehow still remains. And up to literally 10 years ago, we didn't have the options. However, this is just, I think, part of the transition, because the transition will be a lot more profound, particularly looking at the idea of decarbonization. As it's evident, again, given what is happening in the past 6 months, this is the worry is not only about electricity and about decarbonizing electricity. The worry is about decarbonizing the whole energy system. And while you do this, how do you guarantee security of supply? Now, you will know that Europe and large part of the world now is actually being challenged by the war in Ukraine and skyrocketing gas prices that affect the electricity system and basically the heat sector. And these two systems are so intertwined as somehow can be seen in this picture that is showing the Sankey diagram of the UK of the UK system. The picture is a little bit old. It's like 2010. Actually, I have a new picture. But things have not changed very much, particularly in the fact that regardless of how much renewables you put in the system, there is still this chunk of domestic. So there's different colors. These different colors represent three different vectors, the main vectors we have, the main services that we need to deliver: electricity, heat, and transport. Of course, it would be cooling in other countries like this one, but I don't know if you've ever been to UK. It's a pretty unlikely country when it comes to weather and sunshine and everything else. So let's focus on heat, given compared to the UK as an example. Now, you look at this picture. As I said, the one color is transport, one color is heating, one color is electricity. Do you know which one is what? So what is this big one? Is it electricity? By the way, I say this and that because I don't really know the names of these colors. I've always wondered why would the Department of Energy put forward this kind of very strange colors that you cannot name. And I cannot name it in English, I cannot name it in Italian. And if we go through a poll now, I'm sure that nobody can agree in any language about the names of these colors here. So it's just a big mystery. I would have preferred to have a clear green, blue, red, yellow, but then we can't. So we need to name them somehow. How do you want to name this? Let's say green, okay? Whatever it is. It's not green, but let's call it green. Is green electricity? What is it? What do you think it is? It's transport. Do you think this is electricity? This purple one here. That's not electricity, that's heating, all coming from gas. So which one is electricity? Electricity is the kind of pinkish color here. So electricity is very small in terms of energy, whereas transport and gas are gigantic. So the idea of electrification of heating and transport comes from this picture. When you look at this picture, say, how do I actually decarbonize transport and decarbonize heating? That gigantic energy consumption, pretty much 80% on average against 20% of electricity. And then, of course, we say, well, we can actually, we try to decarbonize electricity, and then by electrifying heating and transport, we then decarbonize everything. Well, that is not so easy, but that's another talk. So, but however, when you look at this kind of picture, you really understand that there are transformations that are much deeper than just having renewables in power system, in a grinding system for renewables. However, in a way or the other, we know that most changes will actually eventually happen at this level here. So at the very distributed level, because in order to decarbonize these other sectors, you must do something. Transport must do something. Heating, they are inherently linked to what happens around us. Now, yesterday we mentioned the smart cities and all that. So once you try to electrify everything, decarbonize everything, you end up with a system in which you must have all these new technologies popping on the system. Of course, this is now again changing completely the whole profile of system operation, because you now find yourself with more and more technologies that consume electricity or produce electricity, but also very, very flexible and controllable at the edge of the grid. And that is why when we talk about distributed energy resources and then moving forward, communities, microgrids, virtual power plants, where we have the biggest transformations, the biggest challenges, but also the biggest opportunities, given the kind of context that I'm showing here. And we will move very likely from a system like this one, dominated by unidirectional provision of flexibility, to a system somehow where flexibility might be provided from the edge of the grid to the rest of the system. And it is the rest of the system that becomes somehow less and less flexible. And in fact, you may argue that more and more renewables in the transmission system will actually call for more and more flexibility. So before, flexibility was all coming from the transmission system towards an inflexible distribution system. And now it is the transmission system that is becoming less flexible and asking, calling for more and more flexibility. So when we look at this idea of flexibility from the edge of the grid, transformations again would be substantial. Some of them we're already seeing them, because if you look at what happens at the very distributed level, what could happen? We will have the microgrids, but more generally forms of aggregation. There are commercial aggregations or physical aggregation. For example, virtual power plant, there is a virtual commercial aggregation of distributed resources. But then we talk more and more about energy communities, and more like physical aggregations of distributed resources. They are also they come together with the idea of the customers also playing a key role. So when we look at that, there is a future where the interface between all distributed resources and how aggregated and coordinated and the rest of the system will be such that there will be actual flexibility provision upstream. However, in order to do this, we will also need transformation from kind of passive entity, passive manager of the distribution network to a very active system. And that's again why we call it DNO, distribution network operator. And now we talk more about DSO, distribution system operator. But it's no longer just a network. They need to maintain that. There's our system. They need to actively manage the same as the system operator will do in the transmission system. So once we're seeing all these transformations, then the question arises as to how, if you look at the energy trilemma, all the different distributed resources and different ways of aggregating, controlling, somehow incentivizing distributed resources could provide system support. And I would say two steps actually. One is network support, like kind of local network support, and then system level support that providing system level services. In particular, starting with networks, I think the fundamental question would be how much redundancy do we need across the system the more we have more and more distributed resources. As I said in the past, because you have the unidirectional flows and the passive network, then you would design that distribution network as large as possible to deal with the worst case scenario. So you would add lots of redundancy. But now that you have lots of active resources and flexibility, do you still need all the redundancy, or can you use intelligence to displace assets? So the idea of the smart grid is fundamentally related from a technical perspective to this question. How much redundancy do we need in the system the moment there are resources that we can control or incentivize to operate and then in such a way and then displace assets? But when you look at that, start thinking that things that we've done in the past, like N-1 redundancy for a distribution field like this, would sound pretty dumb. I mean, we cannot say this because, of course, we had a very, very large system for 100 years. But with the new technology, this doesn't make sense because you have, like this is a typical design, N-1 design distribution feeder. You have two feeders there, basically oversized, there's a double size for the feeders, because in case there is a fault in the network from here, you want to be able to close that normal point and backfeed from substation. Obviously, in order to do this, for the worst case condition means that that network can only be utilized at 50% capacity. So what you do is you build two networks. Now, how often is a fault happening of that extreme fault? Well, probably never, or maybe once every 5 years, once every 10 years. So what we're saying is that because of the faults that might happen once every 10 years and because how much worth is reliability to customers, we double the network. And of course, with a huge cost, right? However, today, because we didn't have other options, today, what we do is, okay, how about having a microgrid that in case of a fault, it can of course disconnect from the grid and potentially also supply local customers around there. So the moment that you have this, in the old style, the kind of predict and provide philosophy, you want to connect new areas, you need to add more network. Now you say, well, you want to connect a new area, why aren't you operating the moment we have active resources in there, as a system that in case can go landed if needed some form of demand response, doesn't have to be necessarily microgrid. And then provide support to the rest of the system. So this is beneficial for the system because you save the infrastructure. It's also beneficial for the customers because now they acquire reliability premium in a way, operating like this. So it's extraordinary in a way how you can think of how much the system could change if we could really use these resources. Of course, you say, well, but how much does it cost? Is it really better than having more assets? Because say microgrids are expensive and batteries are expensive. And then the other question is why, if it's so good, it's not happening? Well, I have a very clear answer to this, which I will try to share with you. The first point to understand this is the fact that moving forward, we know the future less and less. So this is like coming from distribution network design of 10 years ago, again in Manchester. And then these are the predictions about load growth for a local substation in Manchester. Now, how do you design? There are basically 5 scenarios of load growth. So how do you design a substation against those scenarios? Now, in the past, there was only one scenario because you could just project load growth and it's it. But now, say, okay, I've got load growth, but what happens if in the area I go to more and more PV systems popping in? Obviously, the load growth will not be there because it would be largely displaced by PV and batteries and all that. So that's how somehow they came up with this science. Now, traditional design is deterministic. Again, there is a future. There is load growth. You design for that. Well, it no longer that no longer works. And if you look methodologically, this is what happens. Imagine that you have a toy system. Really. Imagine that you have this 3-bus system, and you need to supply this demand, and you would like to connect solar and wind, and you want to understand what is best to connect, for example, wind here, to connect solar here, and then do you need to reinforce the network? So traditional studies will go with deterministic assessment of the cost of wind, cost of solar, cost of network, and let's say you would end up with a solution like this. So okay, you build wind here, and then you build also a transmission line. But then this would be thinking that wind will have some cost and solar will have some cost. What if, and then of course, this is equivalent to creating redundancy, which is like, it's always like this. Whenever you design this kind of deterministic way, the solution is always build more network. Now, you start looking at a problem under uncertainty and say, well, actually, I don't know if the price of PV is really going to be this in the next 10 years. Maybe it will be 50% or 100%, largely lower than it is, like it is actually developed. So when you look at this problem, actually you find out that if you model it mathematically, and I'm sure many of you would know better than me things like stochastic optimization of that. So if you do it mathematically, what happens is that instead of building a network, the moment that you introduce uncertainty, for example, in the cost of technology, what you would do is you will start building, in this case, the candidates were two smart technologies, one a quadrature booster and the other one a battery, that basically would displace network. So say network provides spatial arbitrage, quadrature booster also provides some form of spatial arbitrage by allowing to reroute our flows, while battery provides temporal arbitrage. When combined together, these two technologies basically do better and more flexibly than a transmission network. And if the future is not what we expect, actually do not represent a stranded asset like a network might be. So magically, if you change the methodology from deterministic to stochastic, you move from a future that sees networks to a future that sees intelligent technologies, flexible technology. So you move from redundancy to flexibility. But in order to move, you need to change the approach to system design, basically. And with this, I mean, we've done this in different contexts. For example, we designed this kind of tools that, in practice, we look at the financial environment correspond to real options model. So the people in finance will use options in the mathematical model of options to do this kind of studies. Engineers would use a real option model that in practice turns mathematically into some different forms of stochastic optimization. So done this for substations in Manchester, and now as a recent exercise, we're actually doing this to plan the whole Australian transmission system with transmission system operation. Because again, if you look at the Australian system and say, okay, how do you plan the transmission grid against all these multiple futures? Like, okay, coal, what can happen to coal? There are many futures. Distributed PV, what will happen in the future? And then solar PV with all technologies. There are multiple futures for all these technologies. And then, of course, you look at gas. It's like, gas is so difficult to predict. This is, okay, I just got one scenario, and then whatever. So how do you plan a transmission system to transfer gigawatt and gigawatts of electricity under this uncertainty? So again, we basically apply this kind of modeling that we developed now doing for the transmission system. And what is the results again? That the moment that you do stochastic planning, transmission, you invest less and less into networks, and you invest more and more into storage. Distributed storage, batteries, and some type of storage, depending on the kind of cost function of that. Now, I'm not going to discuss the picture. You can have a look at the paper case, but the message is really, the more that you bring intelligence to the system, intelligence is not only technology, it's also intelligent planning, then you really see the value of these resources popping up in the system. I'll skip this because I want you to go to this, sorry. Yeah, I want you to get to this point here. That is actually the highest of uncertainty, the greatest really. How do you plan a system for rare events? I mean, by definition, an event that is rare is very difficult to predict. Right? That is why we call about black swans. Do you know where this comes from? Where the idea of the black swan? Do you know why?
Yeah, like what happened in Texas last year is a great example.
Yeah, that is a black swan.
Yeah, sure.
And the word black swan, now why do we talk about white swan and black swan?
Rare. You don't see black swans.
Exactly. So this comes from the Latins. So there was a saying in ancient Rome, say, as rare as a black swan. Because black swans do not exist in Europe. By the way, as rare as black swans, this was referred to a nice person. So a nice person would be as rare as a black swan, because they will not be a nice person in ancient Rome. Black swans do not exist in Europe, right? So you had to wait the 16th century for the Dutch to get to the west coast of Australia to find out that black swans do exist. So how can you have how can you plan for a future that you have never seen, but there might be? You cannot exclude anything. This is the idea of the black swan. And as Ben said, the Texas case was really like conjunction of events, unprecedented, unforeseeable, a real black swan for the Dutch arriving and seeing black swans on the west coast of Australia. I know this kind of events, and unfortunately, we've seen more and more. So when we talk about reliability now, then we need to talk more about resilience. This idea that we need to deal with extreme events that we never seen. So what do we do with this? Do we use more networks? With more network redundancy enhanced resilience. I'm sure many of you will say yes. Let's build more network. Yeah, that's why we need to read the old classics. In this case, not Roberts, I guess, a bit more modern old classics. It's a very nice paper by Kirsch and Sturbach. Why investments do not prevent blackouts? There's not at the times when we were discussing about resilience, it was like a more general case, saying that eventually you put more network, the system will just be pushed more and more, and the larger system, more interconnected, actually will come under extreme cases much closer to different forms of stability limits. So the more actually you build your system, the more you will push it, especially the market actually economically will push it, because you want to squeeze more and more out of the system, and the more actually under extreme scenarios you may run into blackout, because you will operate closer to your stability limits. So there's no solution, you know. It's gentleman on the left always beats the gentleman on the right. Do you recognize this? This is Gustav Kirchhoff. You know, Kirchhoff law, so everything we do with our system is pretty much coming from this. This is Adam Smith, father of economics, right? So physics always beats economics, and you can build a network as large, there will be a market, we do your things, and then nature comes, we disrupt everything. Again, Texas, everything else. So this is the heart of resilience. We need to be smarter than just building networks. And so what we do is somehow we think with, again, another trilemma, so-called resilience trilemma. Do we make the system stronger, bigger, or smarter? So do we reinforce the network? Do we create redundancy? Or do we actually introduce new technologies so that we understand that actually you can't build a network strong and big enough to resist, for example, wildfires and earthquakes and all that. But you can build an intelligent network that fall graciously and recover fast. And this idea of this picture that I sketched, you know, rather than say try to prevent the system from falling, you actually limit the degree that this system will fall during the event, and then you try to make it recover very, very fast. And this is the idea of having more microgrids in systems. Okay, there is a big event, you split the system, you control the system, you split the system, and now the system is lost of balance, and then they can come back together. This is the idea of, you know, in the future, how we could see the system would evolve. But this is the only way to provide economic resilience to any foreseeable and unforeseeable situations. And again, when you look at that, you will find out that if you think by stochastic optimization, so this kind of planning under uncertainty, actually you extract value for technology to provide resilience. Because the big question, again, the other big question I mentioned before is, if it's so valuable, why isn't it happening? And again, it's because the methodology that we use to price networks and technologies is wrong. Is the regulatory environment that we use that is wrong. Because if you use the regulatory environment, if you develop a regulatory environment that would use more this kind of again, stochastic planning versus deterministic planning, then you will find out that technology will be boosted, and this big issue of how can I invest into something to prevent you know, system collapse that might never happen. Actually, there will be an answer to this question. By the way, when I talk about stochastic planning, this is not the kind of things so scary that some of you also might think, because you can do stochastic planning thinking in a stochastic way and program it in an Excel file. I mean, some of the tools that we developed are programmed in Excel to give it to network operators to actually be able to do very simple planning, but in a new way. So it doesn't have to be crazy mathematics that nobody understands, like the typical transaction paper. That is good for something. The real world requires other ways of thinking. So we need to take the thinking and translate it into the real world. This actually happened in Australia. We're doing this more and more. And in this example that is taken from bushfires again, and the details are in this recent paper. There was in this very nice Orange magazine special issue about wildfires. If you look again at this kind of thinking, you will realize that if you plan a network according to N-1 security, imagine you have a rural community here. So the typical way of planning a network would be you build a network to supply this rural community. Only to find out that there can be a bushfire there happening once every say 10 years. And they say, well, okay, it's rare anyway, we don't care about it. Then it happens, and what you find out is that once it happens, there is so much impact in terms of value of lost wealth. They say, well, maybe I should have thought about it. And then if you think about it, if you plan with this idea of bringing resilience, the solution would be completely different. The solution would be, instead of having a network in the bushfire area there, actually you build less network in the bushfire area, you build more network, and somehow you create a loop here, and of course you build more and more distributed energy resources. And then the cost is actually not very different from the base case, and the reason why it's not very different is because the moment that you have more and more distributed resources, they can also play in the market, that can provide a number of system services and network services, and somehow you create a business case also for distributed resources. But in order to do this thinking with the current methodology that we use for cost-benefit analysis and a regulatory regulated investment, this doesn't work. We need to think in a different way. We need to introduce form of risk aversion, so to speak, in the system. Eventually, distributed resources here provide some form of insurance policy against extreme events, and somehow bring overall less redundancy and a smarter grid. But to do this, again, you need to change the regulatory environment to allow you to do that. But we know how to do it, and in fact, it's been done. And now, and this is the very nice thing of this, that you can also start thinking for the new systems you need to plan, particularly, for example, let's say electrification of rural areas. And this is, I'm sure that many of you will recognize this board, this like projects that we had some time ago with Garnish, Western Manchester, and Western Africa, and Sarawak Energy, trying to understand what is optimal design of a mix of networks and distributed resources microgrids if you want to electrify the whole island. So, and this kind of what is, and of course there's lots of flooding and everything else happening in the island. So what is the optimal design of this system somehow? So what we found out eventually with the project is that it's even more complicated than this, because you need to add a fourth pillar that's got to do with social aspects and the fact that you need to involve also local communities in the picture. And somehow we move from an energy trilemma that already was very complex to an energy quadrilemma that also involves somehow social aspects and local communities. So, just to conclude, there is a huge value that distributed resources could bring in terms of flexibility services to then provide reliability and resilience. However, the regulatory environment that we have throughout the world does not allow to unlock this potential, because basically we cannot really extract the real option value that is intrinsic in this flexibility from these technologies. And the current regulatory framework is not risk averse, it's a risk neutral way of thinking. And like this, you can't plan for extreme, rare, high impact local ability events. On the other hand, the moment that you think risk aware and this form of probabilistic planning, then non-network solutions and distributed resources emerge naturally as the best possible investment that you could make. However, because this is really happening at the edge of the grid, somehow what Wayne was saying yesterday is really resonating. You need to have the customer at the end user in the loop. It's no longer just an engineer problem that would be easy. You need to understand how now end user and customer is to be involved. Also, because many of these technology would really help it in our lives. Somehow I think that I feel sometimes, at least I wish we were like this. Do you know who said this? Well, I mentioned Tesla before. This is the other one. This is Thomas Edison. Do you know why Thomas Edison said this? I know I'm running out of time, so I'm using all this. Do you know why Edison said this? Well, Edison is famous for the light bulb, right?
Yeah.
And then, of course, Edison invented this light bulb, and then said, well, I really want to make money. His life was a great entrepreneur. I really want to make money, but I can't make money because nobody's got electricity. You know, this light bulb needs electricity, but electricity doesn't exist. So he said, okay, let me actually invent electricity, let me build electricity. So he built the power station in Lower Manhattan. He built dynamos, he built electricity system to do what? Not to give electricity to humanity, to make money out of light bulbs. And of course, when he did that, he also realized that this electricity is really inefficient because there is lots of heat that is wasted. So do you know what Edison's business model was? The thing that you would go to customers in Manhattan and say, this is your bill, kilowatt hour, daily charge. And the people say, what are you talking about? I have got candles. You just say, look, you give me this much every month, and I give you light and heat. That was Edison's business model. It's like, we are now going again to the service-driven business model, flat tariff, and I give you everything. That's what Edison was doing. Like, you don't know what there is behind, it's a black box, but you will see light, and you will have heat, because the first cogeneration plant in the world was actually the first power plant in the world. So Edison power plant was a cogeneration plant. So again, we're just reinventing the wheel. We go back to the future once again, and I think there is a lot to learn. And somehow we are now, again, in a way, doing like this big transition. There is a lot to learn. So thanks everyone, and yeah, be very happy to talk with you now or later. Thank you.
Well, thank you very much for very informative, energetic, interesting presentation by Prof. Pierluigi. So I think I would like one question from the floor because we are running out of time. Yes, please, Swing.
Yeah, so I'll go it loud. So Edison would not be, excellent presentation, by the way. Edison would not be a big fan of LED bulbs, right? No heat. But yeah, I totally agree with you. We need to change the regulatory framework for sure. With the bi-directional flow of power now, everything's happening at the distribution level. When I first got involved in the industry in the 1990s, I remember commenting to my global colleagues at the time, well, should we be concerned about distribution? Several of them, even older engineers, said, no, those are all disposable throwaway things. We're just concerned with transmission. And at the time, that's where all the money was being spent, right? Transmission and not distribution. But I read an article last week that now 8 times money is being spent in distribution versus transmission. So it's great. So you covered a lot on grid edge, and just found out this morning this has been announced, and I wanted to share it with everybody here that IEEE PES has made an announcement that we are going to have a 3-minute PhD dissertation challenge. Even if you already have your PhD, you can apply for this. It invites PhD students and recent graduates to participate for the chance to win the Grid Edge grand prize of $5,000 US. It's, I think, the largest competition IEEE has ever had. This competition will provide an international platform, so everyone is invited to attend and contribute, submit, I should say, proposals for all PhD researchers in the fields related to grid edge technologies, and you covered so many of them up there today to present their projects. This award recognizes not just quality research, but also provides a unified platform to share technology innovations and exchange ideas between academia and industry. The presented ideas should demonstrate economy, society, environment, or technological advancements. There's a whole announcement about another good education, but any of you that know either PhD candidates or recent grads, please invite them to participate, and we would love you to come present the same presentation at eGrid in Zealand if you'd be willing. It was just chock full of so much great information, and I appreciate you mentioning the recent edition of the wildfires edition. That's something now that really is affecting the whole world. I just talked to some colleagues in California. The fires there now are out of control, and you had a great article published in that special issue. I think it was about 3 or 4 months ago. So refer back to that. Any of you, it's online, it's in the PBS Resource Center. This paper is in there along with many others. But thanks again for sharing.
Thank you.
Really appreciate the presentation.
Thank you.
Okay, I think we are up to the session. Please join me to give round of applause to our speaker. So, okay, Prosperity, please remain on the stage. We are going to give some token appreciation for you. Okay.
Thank you, Professor Dr. Pierluigi and Professor Insinyur Dr. Ahmad Faris. Ladies and gentlemen, let's move on to the next technical talk. Without further ado, I would like to invite Associate Professor Dr. Jasmani to introduce our speakers today. Please welcome Dr. Jasmani.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning. So I would like to introduce our next speaker, which is Mr. Muhammad Syamil bin Ramli. So a little bit background about Mr. Muhammad Syamil. So Encik Muhammad Syamil actually started a career as a substation operation and maintenance engineer, transmission division with TMB in 1997. And after that, being appointed as the head of the grid maintenance, Selangor, grid TMB in 2015 until 2017. And during that period, he responsible to ensure that the high reliability, availability, and security of the grid system. And after that, being appointed again as a head of the grid asset strategy under grid TMB. And during this period, between 2017 until 2020, Mr. Muhammad Syamil have developed a risk-based maintenance strategy for the grid division with the aim to optimize the maintenance by balancing cost, performance, and risk. And currently, Mr. Muhammad Syamil has been appointed as a MTM at MTM as a Chief Operating Officer, COO. And he is responsible for the business operation and delivery of 11 kV up to 1132 kV product and service. So without further ado, I would like to invite our next speaker, which is Mr. Muhammad Syamil, to give a talk on energizing a sustainable tomorrow. Please welcome.
Thank you, Prof. Jazrul, for the kind introduction. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. We had a very good presentation from Dr. Pierluigi earlier, and I believe my presentation is a little bit connected to him because he talks more about planning, and I will talk more about the product of the transformer, which is important to the network. Of course, transformer is very small compared to the network in comparison, but I think transformer is still an important component moving forward, and also in the transition journey of sustainable development. So first and foremost, thank you to the organizer for having me today. I think we at MTM, as the Malaysian transformer manufacturing, we proudly support IEEE and on this POWERCON 2022, and appreciate for the opportunity given to us to give a presentation at this conference. A little bit about us. We have this year we our 45 years in operation. We were developed in 1977, and then we have a partner on Bonalong, Scotland, if you are aware of that. And then we have a partner with ABB Transmission, ABB T&D, back in 1995. But starting from 2007, we are a wholly owned subsidiary by the utility at the National Berhad. Currently, we have a 579 workforce, and we are located in 3 main areas. We have a plant in Ulu Kelang, that is for our distribution transformers, and we also have a plant in Kapar, which I think is scheduled for a visit this afternoon. That is mainly for the high voltage transformers on the 1 to 2 kV. And our corporate office is located also at Ulu Kelang. So briefly about our business, I apologize if this one bored you, because knowing the participants are all technical people, in the academics and industry people. But I would like to take this opportunity, just since many of you come from all over the world, and I think I would like to take this opportunity to introduce a little bit about my company. So our business, of course, being a transformer manufacturer, we cover the whole asset life cycle, coming from the development of the transformer, design, development, production, testing, and installation, commissioning, servicing, and finally the retirement as well. So we cover the whole asset life cycle from the cradle to grave. So in terms of products, as I said earlier, we covered the distribution transformers from 11 kV with a various rating from 200 kVA up to 1,500 kVA. We produce a 3D wound transformer, and then we have a power transformer for the 32 kV, 30 MVAs, 15 MVAs, and 7.5 MVAs. And finally, the product, our recent product, starting from 2020, will be the 132 kV power transformers. In addition to that, we also do services and projects, remanufacturing and repair, and also, as I mentioned earlier, the retirement of the transformers. The current trend, if you look at the current trend, Dr. Pierluigi earlier mentioned about the evolution of the network, and I believe it also affects the transformer industry as well. Moving forward, what we have seen on the trend is many utilities or the government policies, they are requiring to be more efficient, and then also environmental friendly transformers. And also the industrial and commercial growth have put a higher demand for the distribution and power transformers. And not forgetting that, because the power network in Malaysia have grown since 1970s, and now we have reached an age where we have reached a stage where many of the assets are aging, and we need to do some refurbishment and replacement of the transformers. Notwithstanding that, with the current expectation of the global in terms of the efficient consumption of power, reduction of the carbon footprint, and also digitalization, We are also working together with Tenaga Nasional to produce smart transformers. This is part, when you have smart transformers, you can collect more data, and that data will be fed and then can be used in terms of better planning for the network. So what I'm going to talk today will be more on the greener future through the development of a 3D wound core distribution transformer. This is our recent product that we are collaborating with Tenaga to ensure that we can achieve what we call a low loss transformer and reduce the losses in the power network. 3D wound core is a kind of wound type core transformer. I think many of us are familiar with conventional transformer, but 3D wound core is a kind of wound type transformer. It is pieced together from 3 single core and like a triangle. And then the 3 leaf display like equilateral triangle, and every single core is wound with several trapezoid-shaped silicon steel strips continuously in order. The trapezoid-shaped strips are cut by the special curve slitting machine, and the core is then formed using a forming tools and then annealed inside a high temperature oven to give the stability of the core. In terms of the structure, it is like a normal transformer. We have the HV terminal, LV terminal, the winding coil, 3D wound core, and then lifting up to lift the transformer, the upper clamp, lower clamp, tapping, stable, cooling fans, and WTI. It is same as a normal transformer, but what we can say the difference will be in terms of the structure, which will be explained or shown on the next slide. On your left will be the conventional transformer core, it's 3D, right? And then on the right side is the 3D wound core. You can see the difference in terms of the, you have the core and limb on the left side, but the equilateral triangle on the 3D wound core. Then you can see the magnetic circuit for the core, different distribution for the 3D wound core. Two different core structure. You can see in terms of the cutting, the wound core versus the laminated core. The wound core have a unique cutting. Through this unique cutting, it have a reduced waste. So you reduce the waste for the core. And then in terms of the core rounded corner, this gives more material saving. So when you put the copper foil on top, then we have a reduced copper as well. And then in terms of the cross section and the 3-phase magnetic circuit, the 3D wound core give a more balanced magnetic circuit. In terms of the process flow of manufacturing 3D transformer, as I mentioned earlier, it is similar to a normal power transformer for distribution transformer, but the manufacturing technique is slightly different in the sense that you have a slitting coil first. This will be the slitting coil, then it will be slitted here, and after that will be rolled together to form the 3D wound core. So that it will be put into the vacuum impregnated chamber to give the strength. And after that, it will be taken out, and depending on the whether it's for all immerse or gas resin, and the copper will be onto the 3D wound core. Instead of for a conventional transformer, it is separated. You build the core, you build the winding, and then you assemble them. But in here, you wound the copper on top of the 3D wound core. And once we have the copper is wound on top of the wound core, then you can tank them inside the transformer tank, and ready for testing and so on. Similarly, it's been done for the gas resin transformer as well. So in terms of the comparison study, For a conventional silicon steel stack core, the no-load loss is about 1,500, and then the load loss is 7,516. The NOS pressure is about 57.9, and the weight is 3,190 kilograms. But with a 3D silicon steel wood core, the no-load loss is lower at 1,341. The load loss is 6,434. The NOS pressure is 43.7, which is much lower from the conventional transformer, and the weight is only about 2,646. So there will be a lot of reduction if we do a comparison on this. So you can see we have a saving of about reduction of 160 watts for the no-load loss, 1,082 watts for the load loss, and 544 kilograms for the weight. In terms of the efficiency, the slide shows the chart on the transformer efficiency versus the loading. Of course, for a normal distribution transformer using network, the loading is around 50 to 60%, and this is where the transformer efficiency is being looked at. So if at 50%, the 3D wound core efficiency is around 99.268%. Versus the conventional or transformer of 99.162%. When it is stabulated at the various transformer loading, then you can see the difference of the efficiency of a transformer. Not much if you look in terms of the curve, but eventually the 3D wound core gave a better efficiency, and also in terms of the weight. In terms of the environment, we look at the countries all over the world in terms of the CO2 emission on 3-year average from Japan to India. And Malaysia, for Malaysia at the time, it was 638 gram for CO2 per kilowatt hour. But if we look in terms of the transformers, for a conventional stack core, when you put a comparison in terms of the transformer capacity, load loss, the annual energy loss, and CO2 emission rate, you can see that the 3D wound core have a better, how would I say, performance. For example, as I mentioned earlier, the no load loss, the 3D wound core is 1,349 compared to 1,500 for the stack core. And in terms of CO2 emission rate, in terms of the annual CO2 emission per transformer ton per year, we are looking about 16.58 ton per year for a 3D wound core. And then for over the lifetime, over 30 years, the reduction is the number of CO2 emission is about 580.3 ton. And if it is compared to the conventional stack core, the 3D wound core have a reduction of 12.2% compared to the conventional stack core. So in terms of the environmental friendly transformer, the 3D wound core is better than the conventional transformer. So we have done a few tests with our parent company or utility to see whether it fits with the current design or current requirement. So because when we develop a transformer, we must ensure that it fits whether we can do a direct one-to-one replacement or also fit with the current planning guideline by the authority. So this is some example of the oil immersion transformer installed at the TNB substation. So you can see how it is installed at the substation and it fits the requirement. So this is a field trial at one of the substation in Tenaga. And similarly, we carry out a cast resin dry-type transformer in TNB substation as well. So you can see that it fits the requirement, and the field trial went on successfully. So in summary, the advantage of 3D wound core is energy saving based on our study at the moment. It's energy saving is with naturally low losses. It also gives material saving in terms of the steel and also copper. and it is also relatively quiet, with a 7 to 10 decibel reduction from our conventional transformers. And then with the 3D triangle structure, the magnetic balance is, the three-phase magnetic is more balanced. In terms of the integrated solidification, when you push the vacuum impregnation, it gives an excellent reliability. And then we also noticed that the transformer with this technology that we have worked on, it can be used for other special application as well. What I'm showing here is the serial guna pakai for a transformer to enter or to be operated in the Malaysian power system. We need to ensure that it has a certificate from the utility. So this show that both our transformer, the oil immerse and also the cast resistant transformer, has passed all the stringent tests and the field trial, and have been issued a CGM guna pakai fit to use certificate. In other words, right? That will conclude on the greener transformer, our product. But in addition, in ensure sustainability, we will not just produce the 3D distribution transformer. We'll also look at the other initiative or product and services that we can offer or give to our parent company or utility. We have started 2 or 3 years back ago on synthetic ester biodegradable oil. So this is the advantages of this type of oil, replacing the mineral oil, will be non-corrosive and also environmentally friendly. It has a higher fire point and is very low in maintenance. It is additionally a high moisture tolerance and enables the extension of cellulose insulation life. What we are receiving more and more orders for this ester biodegradable oil, because the transformers that use this oil will be used in the building, because for the fire requirement from the authority. So compared to the normal mineral oil, if you remember at the earlier presentation, you can see transformer caught fire. But with using the ester biodegradable oil, with a higher fire point, and the risk of catching fire is very much reduced. In terms of reducing carbon effect or reducing the carbon that produced during operating the transformer, with a vacuum tap changer. Normally, on the old tap changer technology, we have arcing inside the diverter switch, and every time they change the tap, so that produces carbon. But with this new, not to say new technology, but with this technology from the MR or other OLTC provider, they use a vacuum tap changer, in the sense that the arcing or the switching is done in a vacuum chamber, vacuum flask. Hence, there will be no oil arcing inside. So what happened is the maintenance interval will be longer. Okay, you don't have to maintain the oil much longer. But in the Malaysian condition we have to be worried on the moisture as well, because as you know, Malaysia is at 80% high humidity. So yes, we don't have arcing inside the oil, but we still have moisture. So hence, from time to time, we need to monitor the condition of the oil. The other service that we support tenaga will be on prolonging the transformer life. So it's just like a normal car. When you reach certain years, you need to refurbish them, you need to overhaul them. So this is what we do with the most of the transformers. So what we do is we do major service of the transformers, replacement of the transformer accessories, and then maybe install some OLTC online filtration. Because for the older transformer using the older technology on the diverter switch, we still use arcing. We need to reduce the outages, because nowadays the demand for reliability or the availability of the transformer is higher. So we have to ensure that the monitoring and maintenance of transformer and monitoring of the transformer to be done online. So what we have done, we put an online filtration for the OLTC. so we don't have to take an outage or shut down to maintain the transformer. And in terms of accessories, from our study on these transformers, yes, no doubt the transformer, the active part can last 30-40 years, but most what the fail earlier would be the accessories. So once the accessories fail, it also will bring down the transformer as well. So that will impact the reliability of the transformer operation. So instead of spending, on the building more transformers, what we do is just replacing the accessories. This is based on our years of study on the data collection. In addition, we also look digitalization. When we replace the accessories, we replace with a newer generation of accessories that can communicate digitally with the IEC 6550, with a digital substation that will give you visualization on the transformer. So again, it's all about visualization and data collection. And this data is stored in Tenaga database for future planning and also asset monitoring. Somewhat similar with my explanation earlier, visualizing a power transformer. We now have, again, transformer is just a transformer. Step down the voltage, transform the voltage, and so on. But what creates value will be how efficient you use the transformer. You can really push to operate the transformer. There are certain areas where you can't install anymore, or you cannot introduce any more redundancy because of the constraint of space and so on. But this is where, by having accessories that can connect to the transformer, you can have more information. You can have the temperature, you can have the oil condition, and then you have the bushing condition and so on. So from all this data, this data can be fed to the operator, and they can really operate the asset to the maximum or optimum, and also plan for what's the best to operate transformer. And we believe by having all these accessories and visualization, it will help in the power for the power system in the future, because for distributed energy generation, like Dr. Pierluigi mentioned earlier, they're full of uncertainty. But how do you tackle uncertainty? By having visualization, real-time information. So that gives you some confidence level to ensure that we can move together in terms of the reliability or changing towards the distributed generation. Right. That will be what are the services that we produce or we provided to our parent company to ensure that we support them in terms of asset management and also sustainable tomorrow. I believe that there will be a visit to our plant in Kappa this afternoon, and I would like to share some information about our facilities. So it's an environmental friendly plant. We are ISO 14001 certified on environment, and both our plant in Kappa and also Ulu Kelang are equipped with solar panel. So the one in Kappa is equipped with 945 kilowatt solar, and whereas the one in Ulu Kelang is 532 kilowatt solar panel. So that leads to this is also our aspiration together with our parent company to have a net zero on the electricity generation within the MTN factory. In terms of the plant facilities, as I mentioned earlier, there are two facilities, one in the Ulu Kelang factory. The Ulu Kelang factory is focusing more on distribution transformers. Of course, we have all the winding transformers, we have the winding machines, and the core table plate, and then we have vapor filtering oven and high voltage testing laboratory. Similar to the one in Kappa, which is Kappa factory is the how should I say, has been in service in 2019, so it's relatively new, and is equipped with state-of-the-art technology. We have the winding machine in the humidity control area, and then we have an assembly room as well. It's a proper stacking area. And then we have a dedicated welding room with air pollution control. We have a vapor filtering oven, and also the high voltage laboratory in humidity control and fully enclosed fabrication, which we believe is the first one in Malaysia as well. So talking about the high voltage laboratory, the high voltage laboratory is ISO IEC 17025 certified since November 2021, and it can conduct the power transformer test in accordance to IEC 676-1. Okay. The equipment in the high voltage lab is very, I would say, we collaborate with the company in Germany, it's Highvolt. So it is designed for full test for 90 MVA, 132 kV, in accordance with IEC 176. It is equipped with the AC resonant test system for applied voltage test. And it's also equipped with test system for transformer testing, which can carry out the losses measurement, harmonic zero sequence in this voltage, line terminal, AC, temperaturize and amplifying current and so on. And also we can conduct the impulse test system for the lining impulse, switching impulse, and chop wave as well. So this is why we say this is the only high voltage laboratory with such facility in Malaysia. Having said that, we are also embarking on the transformer recovery management, because with the circular economy has been meted out. So we want to ensure that we reduce our waste, and whatever transformers that can be recycled or we recovered, we will do it at our plant in Kapal. So we also have a mobile transformer. So again, we see the pattern of having a mobile transformer, a unique one. Why? First, it's being used in terms when we want to replace a transformer or refurbishment of transformer, or we want to upgrade a grid substation. So you need a mobile transformer. The second one, it gives you flexibility on the power system as well. You know, when you need an urgent power supply, but it cannot be completed in time due to some regulations, and implications by the government, by the local authority. So what we can do is we can provide a solution on the mobile transformer as well. So this is where we try to be flexible as well. Like what Dr. Pierluigi mentioned earlier, is flexibility and reliability and affordability. Always, yes, this is the energy trilemma that we are looking at. So not only in terms of our planning, but in terms of operation and connecting the public to electricity, we have to observe this as well. So I would like to end my presentation here for today. I really thank you for the attention given to me and for the visit this afternoon. I would like to welcome you to our factory for the visit, and I hope you have a good time there. So with that, thank you.
All right, thank you very much, Mr. Simon, for the very interesting topic, the transformer and just the latest technology that we have here in Malaysia. So I open to the floor if you have any question to our speaker. Maybe one question. Yes, please.
Well, thank you very much for all of us for enthusiasm. I would say it's refreshing to see the work that you guys have been doing. One of the interesting things that you were presenting, that I think there are so many things that you were presenting, but at the beginning of the platform before, I think you were trying to bring the I would invite you to bring the concept of the community, because even in the 6780, there's no definition of people. Okay, that's the first thing. The other one, you were talking about Esther. And one of the things that we try to deal with different people, different users in the field, is people is trying to move from the mineral oil into Esther in the same transformer. So it's the first stop to manufacturing, right? And I would like to have a little bit of your work on that, because testing is going to be completely different, right? We're going to different type of installation. That's one thing. The other one is viscosity will be different. Temperature for application will be different. And I think the last part of the question that I would like for you to comment more than the question, comments from you as well, is looking into the digitalization of the platform. digitalization could be extremely wide, right? And you can monitor even the humidity outside of the transformer. And you can monitor everything you want. But what is really needed and when it's really needed, right? Because there's online testing, there's a lot of online testing, there's a whole bunch of data, and there's lots of faulty alarms, I would say, as well on these devices. So what is your point of view on that?
Thank you for the questions. Three questions, I believe. One for the 3D wound core. On the 3D wound core, I think I have made some reservation. I think true. There are not many definition of 3D wound core outside there. In fact, in IEEE also there's a little paper on 3D wound core as well. There are some in paper on C-grade, and still that's on 3D wound core. The application of 3D wound core mostly been used in China, and some in Thailand and also India. So when we embarked on this technology, we did a collaboration with our partners from China, and they showed us the facts and details on the application of transformer. I agree, the definition on the international community may not be as much as a normal transformers, but I think we're going to work on that as well. Thank you. In terms of the ester oil, you are right again. When we talk with our parent company in terms of strategy of having ester oil in the transformer, we are cautious. We are cautious on replacing one-to-one, because as you rightly said, the specification of transformers basically may be different. The way they conduct the cooling of the transformer is different these days. And then with the increased viscosity of ester oil, that may impact the cooling of the transformer. So in terms of the replacement of one, we are very cautious on that one. But in terms for the new transformer, we are actively looking at the viscosity and also the design of the winding to ensure that we have a good cooling or heat transfer within the winding. That's for the ester oil. On the third one, in terms of the accessories or having digitalization of the transformer, again, you are right. What we have done, we work with our utility. We look at the risk. We have a category 1, category 2, and category transformer. Category 1 is the 500 kV transformers, and being the 500 kV transformer is very crucial to the network. We have almost everything on the transformer. When I say everything, yeah, literally, we have this online DGA monitoring, and then we have visualization in terms of the time feature, and then we have pushing monitoring as well for the 500 kV transformers. When I say it's practically everything, almost everything. And then the second one is on the category 2. This is where the slightly reduced criticality, mostly serving the major town center, the load center. Again, we don't have as detailed as the 500 kV transformers, but we do have the oil monitoring and also temperature. And these are all fed into the SCADA system, so the operators can monitor the transformer in terms of, touch wood. If there's you need to reroute the loading or something, they can easily look at the temperature of the transformers immediately. And finally, is the category 3. The category 3 is normally on the remote area, where it's not very critical. And what we do is we still do digitally. We still install, how should I say, visualization in terms of temperature monitoring, because we have the infrastructure already. But the monitoring is not as detailed as category 2 and category 1. So what we normally do is just a temperature reading, and that's it. Temperature reading and OFTC counter. That's all. So it depends on the risk management in managing the grid. So I think that answers the question. Right.
Okay, so we have another one question. Yeah, please.
Thanks for the excellent presentation, and I share my IEEE colleagues' comment about please get active with the IEEE PES Transformers Committee. They meet twice a year. They're probably the largest and most active committee of all of IEEE PES. And there are 2 meetings a year that get sometimes 5 to 6 people North Carolina, like energy, but it's all technical, and I'm not sure if everybody's familiar with the transformer video. Yeah, we can talk to you more about it, but I think the presentation would be interesting to maybe present there, but definitely at T&D as well to share that. So my question is, regarding LTCs, your home line tap changes. I recently heard from one of the utilities in California that had a lot of DERs, that their tap change was changing positions. Normally, 5-10 years ago, we changed positions maybe a couple times a week. In this case, it was 100 times in one day. So that LTC now is undergoing a lot of stress, right? And I didn't know if you've done any studies on that or heard of such a thing, but I was just amazed when I read that at a recent conference.
Okay, the number of LTC operations can increase in numbers of ways. First would be the increased demand of the area. You know, suddenly you have a steel manufacturer around the area, and that will drive the voltage. The second one would be what we are looking at, the pattern of this solar panel. You know, this is, yes. So this is where we are still looking at the pattern of it. Well, my colleague, not me, but I'm the manufacturer now. My colleague. Right. So we are getting the data, and we are looking at how we behave with all this renewable energy. As you said, at the moment, I think the target is 20% for Malaysia, but we are still studying how it impacts on the system stability for Malaysia. Because in German, I was told you can have a power swing, very significant power swing from north to south, because they rely on the solar and also the wind and wave. So the wind and wave are located on the north and the southern, and then when the solar is not there or wind not there, then there will be a sudden power swing for German. But in Malaysia, maybe it's not that serious, but we're still collecting the data. So one of our strategy when in tackling this increased number of LTCs, of course, we do a close monitoring operation-wise for the OLTC counters. Whichever have significantly under increase, we're going to attend to it. And for the new ones, where possible or where the investments is so, we're going to retrofit it with a vacuum tap changer. So then we can have higher switching, but less, arcing inside the switch.
All right, so I think I need to end the question now because we have another session after this. So please join me to give a hand of applause to our speaker. So Mr. Shamil, please read this stage forward.
Thank you, Mr. Shamil, for the talk. To conclude the technical talk session today, I would like to invite Associate Professor Dr. Jasru Jasmani to present a token of appreciation to Mr. Shamil. Thank you, Mr. Shamil and Dr. Jasru Jasmani. Excellencies, distinguished guests, ladies and gentlemen, this is the end of our technical talk session for today. We are thankful to all guests, speakers, and participants that has participated in this ceremony. We will have a photo session after this and a coffee break. We will come back at 11 a.m. for the technical session at the dedicated room. Participants can scan the QR code at the registration counter to check the conference program, and you can visit the exhibition by Maker and Imperial located at the front of the ballroom. To all participants, please collect your lunch voucher at the registration counter. That's all from me. Thank you.